Assalamualaikum and selamat sejahtera. In this topic, you will learn several types of basic semiconductor power switches and their characteristics. Before we discuss further, you must remember that all power switches can conduct current in one direction only. In this video, you will learn the voltage and current characteristics of ideal and practical power switches. We will focus on 4 conditions only: during off state or turn off, during on state or turn on, switching activity, and the requirement of gate signal. In all conditions, we will consider a basic circuit consisting of a power switch, voltage supply, and LED bulb. These two figures show the equivalent circuit of the power switch during the off state. The left circuit refers to an ideal power switch, and the right circuit is a practical power switch. In an ideal condition, the inner resistance of the power switch is infinite. Hence, we can consider the power switch to act as an open switch during turn-off. Hence, no current can flow through it. However, practically, there is a small current that flows through the inner resistance. This current is called leakage current. Based on the circuit analysis, we can sketch the current waveform of the ideal and practical power switches as follows. To know the voltage characteristic, we need to apply KVL. Based on that, we can see that both the ideal and practical power switches have the same high voltage across them. The voltage is equal to the voltage supplied by the voltage sources. Thus, we can sketch the voltage waveforms as follows. According to the waveforms, we can describe the voltage and current or VI characteristics of both switches during the off state. For the ideal power switch, the device will block a large voltage with zero leakage current. Meanwhile, the practical switch will also block large voltage but with small leakage current. In summary, the primary function of the power switch during the off state is to block voltage supplied by the power source. Additionally, the product of current and voltage of the practical power switch will cause the device to generate power loss during the off state. This power loss is called the blocking state power loss. Next, let's see the equivalent circuit of the power switch during the on state. For an ideal switch, we can consider the inner resistance equals to 0. Thus, the power switch is equivalent to a short circuit and the voltage across it is 0. At this condition, the switch can conduct high current from the voltage source to the load. Instead, for a practical switch, we can measure the voltage across the power switch due to the inner resistance. The voltage is known as a voltage drop. However, in contrast to the off state, the inner resistance in this condition is very small. Therefore, the voltage drop is also small and it does not affect the operation of the power switch. Hence, the power switch still can conduct high current through it. According to the circuit analysis, we can say that the main function of the power switch during the on state is to conduct high current in electric circuits. Before we sketch the voltage and current waveforms, I need to explain another characteristic of the power switch. It is the switching characteristics that is referring to a condition when the power switch changes from the off state to the on state and vice versa. Keep in mind that the ideal switch changes alternately from the off state to the on state instantly. Thus, we can sketch the voltage and current waveforms like this. However, practically, the power switch requires considerable time to change from the off state to the on state and vice versa. Thus, it creates a time delay before the power switch can conduct maximum current during the on state and blocks maximum voltage during the off state. Additionally, the product of current and voltage during the on state causes the power switch to produce the forward conduction power loss. Meanwhile, the product of current and voltage during the switching activity generates the switching power loss. As you know, power losses can affect negatively the operation of any power switches. Thus, to ensure reliability and efficiency, we need to use appropriate heat removal mechanisms such as heat sinks. Now, let's focus on how to calculate the power losses. In this topic, we will concentrate on the switching power losses only. As mentioned before, the power losses occur when a power switch changes from the off state to the on state and vice versa. According to the previous explanation, we can sketch the waveform of leakage current during the off state and the conducted current during the on state like this. Subsequently, we can sketch the waveform of voltage blocked by the power switch during the off state and voltage drop or on state voltage during the on state as follows. In this graph, the x-axis is referring to the switching time in seconds, and we can see some delay before the power switch is entirely on or off. In between turn off and turn on, the delay is called the turn on time. It consists the current rise time and the voltage fall time. Instead, between turn on and turn off, the delay is called the turn off time. It consists the voltage rise time and the current fall time. Based on the area under both times, we can calculate the switching power loss using this following equation. You may refer to the note for a simple explanation and example on how to calculate the power loss. Nevertheless, based on the equation, we can see that the switching power loss is directly proportional to the frequency or the switching frequency of the power switch, where the switching frequency is equal to 1 over the switching time. Lastly, the next characteristic that will be discussed is the gate signal requirement. This characteristic only applicable to the controllable power switches. This slide shows several controllable power switches that require a gate signal or control signal to operate. Regarding the type of gate signals, thyristors and BJTs require current signals to turn on. Hence, they are known as current-controlled devices. Meanwhile, MOSFET and IGBTs need voltage signals to turn on, and they are called as voltage-controlled devices. For ideal power switches, it's stated that these devices only require a small current or voltage to initiate the on state. However, practically, these power switches require a substantial current or voltage to start the current conduction.